Hi. So today I want to talk about spectroscopy of molecules and how we do that and some basic things about what that is. So what spectroscopy is all about really is to probe molecules' molecular structure by using radiation or EM radiation, so light. And the way that works is that you probably are aware from previous stuff that quantum mechanics that molecules have lots of different kind of states in them. They could be rotational states or rotational states or electronic states. But I could have two states, right, like here, like E1 and E2. And then with radiation, what I can do is I can induce a transition between these two states, right? So I could have, if a photon with the right energy hits this molecule, it might cause a transition between E1 and E2. Okay, and the photon energy has to sort of match that gap. So that's delta E is h nu, where nu is the photon energy. And that's obviously going to be equal to E2 minus E1. Okay, so that's what we do, right? We do this, and you shine your laser on the molecules, and then you see these transitions happen, and then you record where the transitions happen. So you record the absorption or your emission, but you record the transitions, and from that you can figure out a bit about your structure of your molecule internally, right? So a really important thing to understand when you do this is to understand the difference between a spectral line and an energy level or a state, right? So what I've drawn here, these two things are states, energy levels, right? But if I look at a spectrum, so if I was to draw out a spectrum, like here I've got, say, frequency down here, then the line I see in the spectrum, what I'll see is I'll see one line, right? And that line would come in with the energy here, h nu, or the frequency nu, I suppose, right? And so the idea is that what you're seeing in the spectrum is the transition between the two different states, right? You're not seeing the actual energy of the state itself, just the difference between the two states, okay? So two levels gives you one line like this. So it's important to distinguish in your head this thing, which is the difference between an energy level or an energy of a state, which you know from quantum mechanics, and the spectral line, right, which is the difference between the two states, right? And as I said earlier, the energy of this line, let's call that nu, is going to be equal to the difference between the energy levels, right? I guess we should call it h nu as an energy rather than a frequency, right? And so if we know these two energies, right, then we can figure out what the spectral line will look like, right? So let's do that now for a simple system. So let's imagine we have a simple molecule, a diatomic molecule, which is a rigid rotor, right? So let's just say it's a diatomic rigid rotor. So, for example, that means I've got these two kind of balls on a stick, that's R, and this rotates. So we're going to look at the rotational states of this thing, right? Now the rigid there is there because what that tells us is that as we rotate this thing faster and faster, that R is fixed, doesn't change. In real molecules, that's not true, right? In real molecules, that can actually change as the molecule spins faster and faster, but that's for later. Okay, so what would we expect to see in a spectrum of this molecule? Okay, well, the first thing we have to know is what are the energy levels of this molecule, right? And that we know, right? So we know that energy is given by this. J plus 1, where J is a rotational quantum number and B is a rotational constant. What I'm going to do now, which I alluded to a minute ago, that I'm going to change now from looking at energies to looking at wave numbers, which are energies, right? But it's just more common for us to talk about wave numbers than it is about energies in joules. So I'm going to call the rotational term F, right? Fj is B with a little wiggle on top of it means B in wave numbers, times J plus 1. Okay, so those are energies of our states, right? And we could draw a whole ladder of different rotational states, right, like this, going up in J. Okay, so where are we going to see the line on our spectrum then is the obvious question, and then well, it's quite straightforward, right? All we have to say is that our spectral line, frequency nu, right, is going to be between the two states, and the two states involved here, if we assume it's a normal rotational spectrum, the allowed values of the allowed change in J is plus or minus 1. Let's say we're going between J and J plus 1, right? So that'll be F j plus 1 minus f of j, which is going to be b j plus 1 j plus 2 minus b j plus 1. So I can expand that bracket out quite easily. Right, let's just do it now. I'm going to get b j squared plus 3j plus 2 minus j squared plus j. Cool. And get rid of the j squareds. That's a bit minus. Tidy everything else up. And we're going to get 2b j plus 1. So that is the energy, right? This here is the energy of the line we'll see, right? One of these lines. So in our spectrum, if I plotted a rotational spectrum, so say I've got like frequency down here, I'm going to see a whole series of lines, right? I'm going to see a line here, 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 here. And the important point to note is that the line is the difference between two states, right? Two energy levels, okay? And then I think it's often talked about as well is the line spacing, right? So the line spacing, which would be this distance here, spacing, that would be that then, in the same way that the line is a difference between two energy levels, the line spacing is a difference between two lines, right? Two adjacent lines. So in this case, the adjacent lines are going to be j plus 1 and j plus 2, right? So let's just figure out what that would be. We can just use what we've worked out here for the energy of a line. So quite straightforwardly, that's going to be 2b j plus 2 minus 2b j plus 1, which if you work it out comes out to be 2b. Note that the j in here is the quantum number for the lower state, right? That's important here. It's always from the lower state we give the j, okay, in this context, right? So, so we can see that the spacing here is going to be 2b, and there's an equivalent spacing of all the lines, right? So, perfect spectrum will look like a series of equally spaced lines, and the spacing is twice rotational constant. So, you can see from this simple picture that from that spectrum we could figure out the B constant, and from that we could figure out things like moment of inertia of the molecule. If we knew the masses of the two atoms in the molecule, we could figure out the bond length. So you can get some nice information out of this. But the important thing to note is that the difference between a energy level, right, which is which we get from quantum mechanics, the energy of a line in a spectrum, right, and that's the difference of the two energy levels, and then also the line spacing is the difference between the two lines in the spectrum. Okay, so it's important to have this clear in your head, because eventually we're going to start thinking about what happens when you excite, you know, vibrations and rotations at the same time, and then it gets quite confusing if you're not sort of, you know, haven't got the idea down that a spectral line is different to an energy level.